and welcome to Observatory Nights at the Harvard-Smithsonian Center for Astrophysics. Tonight, we are going to look at the intersection of science and art. Now, sometimes science is viewed as nothing more but a dry and dusty collection of facts and figures. In contrast, we often see art as something that inspires us and touches us at a deeper and more human level. Now, astronomy is more visual than many sciences. Just think of the iconic Hubble Space Telescope photograph of the Pillars of Creation, or my favorite, Pluto's cute little heart that we got to see when we greeted it with our first up-close views. But these images can stir us and move us, in addition to giving us new information and teaching us something new. But there is an even deeper connection between science and art. And it's a connection that Lawrence Krauss wrote about in an opinion piece in the New York Times just last week. He was writing about the discovery of gravitational waves. And he pointed out that some people hearing about that discovery asked, what good is this science if it's not giving us faster cars and better toasters? But people don't really ask questions like that when they look at a Picasso painting or listen to a Mozart symphony. Krauss says that science, like art, music, and literature, has the power to amaze and excite, to dazzle and bewilder. And it is that aspect of science, its humanity, that is perhaps its most important feature. I think that you'll be amazed and excited by tonight's presentation. Our speaker, Dr. Henry Trey Winter, is a Smithsonian astrophysicist who has worked on 8 NASA missions observing the sun. His research focus is improving computer simulations of how energy is generated in the sun's atmosphere and in other stars. Dr. Winter also designs video wall displays, absolutely amazing displays that bring the beauty and wonder of the sun and of the universe to the public. His exhibits have been shown in the Cooper Hewitt National Design Museum, the National Air and Space Museum, and the Harvard Art Museum's Lightbox Gallery. So I know that he is going to present something visually stunning to you tonight. Please welcome Trey Winter.
Well, thank you very much for having me. My name is Dr. Henry de Greffenried Winter III. Nobody calls me that. Everybody calls me Trey, and I hope everybody here calls me Trey too. And other than throwing fantastic dance parties, which the crowd got to learn about earlier today, sorry YouTubers, you missed that, I'm also known for transforming data and putting it in a visual way that really transcends, just as Christine said, the dry, the everyday, into a form of art. And I will show you that this is actually not something I've done because I'm a fantastic artist or because I have this special skill that nobody else has. No, I'm just a guy doing some research, trying to figure things out. But my thesis, my point for this whole night is that there are so many overlaps between science and art that it is very natural that once you start the study of one, you're actually participating in the other, whether you know about it or not. Now, this is not something new. This has been going on for hundreds of years. And the reason why it's been going on for hundreds of years is because scientists have to communicate information to others. Now, some of my favorite scientists from years past were Renaissance people, right? We're talking about Galileo, we're talking about Leonardo da Vinci. And all of these ancient scientists actually transcended just science. And in order to communicate what they were seeing, they couldn't reproduce it, they couldn't mimeograph it, they couldn't scan it, they couldn't take their iPhone and Snapchat it. They had to draw it. Right? And that is how they shared it with others. And not only did they make these astounding drawings, which I think are absolutely beautiful, but these are drawings and things done by humans, by people. And along with all the detail of trying to get their points across, they also add embellishments. to the art. Right? So it's these little embellishments, these little touches when you're actually trying to explain something that really shows the human factor of science and the scientists. Now, I'm a scientist, right? So scientists always like to start with definitions, right? So I'm going to start some definitions of what I work with. Now, I work with data. I do a lot of data science stuff. And so I looked up in the Merriam-Webster dictionary the definition for data. So data is factual information like measurements or statistics stuff, right? Facts used as a basis of reasoning, discussion, or calculation, right? So data aren't opinions. They're not what I think. They're not what I feel. They're facts. They're things that we all can agree on based on measurements, all right? And these types of measurements are what I work with day in, day out. Now, I'm a scientist. So what do I do as a scientist? Well, science is knowledge about or study of the natural world based on facts, the data that we were talking about, things we can all agree on, learned through experiment and observation. Again, Merriam-Webster dictionary, right? So very basic, right? Scientists take facts, we try to collect them, and we try to understand our world better based on those facts. All right? Now, if I'm going to talk about the overlaps between science and art, I also need to define what art is, right? So I went through and I scoured lots of dictionaries to try to figure out what a good definition of art was. Turns out, unlike data, unlike scientists, people don't really agree on what makes art. So I'm going to give you a few definitions. The last one is the one I'm going to use mainly, but it's not my favorite definition of art. My favorite definition of art comes from a Supreme Court justice. He was not initially talking about art. We're not going to talk about what he was talking about, but it is a great definition for art. I shall not today attempt further to define the kinds of material I understand to be embraced within that shorthand description, art. We're right there. And perhaps I could never succeed in intelligibly doing so, but I know it when I see it. So it's usually that last part of the quote that everybody remembers. I don't know what art is, but I know it when I see it. All right? And that is probably the truest definition of art, because it is something on a very personal level. It's something that impacts you. And what might impact you might not impact somebody else the same way. But since I'm talking about facts, I'm talking about the overlaps, that's not really a useful definition. I think it's a good definition, but it doesn't really help us advance the conversation. So let's try another definition, shall we? All right. Art refers to anything that is made by someone who is considered to be an artist. Yep. That is one that's often used by artists. It's why Lady Gaga can get away with wearing a meat dress, and Christine said I couldn't. Again, that might be true. Not very useful for the conversation we're going to have today. It's an actual definition. I put a reference. You can look it up. All right, so what is the useful definition? What's the definition that we're going to use today? Well, all the other definitions are valid, but this is the one I think is useful today. The expression or application of human creative skill and imagination producing works to be appreciated primarily for their beauty or emotional power. All right, and I like this definition, right? And some of the reasons why I like it is because it really focuses in on the human aspect. There needs to be someone actually making the art, right? Producing a work. You've actually made something, and it is appreciated primarily for something. In this case, we're saying beauty or emotional power. For me, I find science to be a lot of the same. It requires human creative skills. It requires imagination. And we produce works, but they're to be appreciated for trying to push further the boundaries of human knowledge, to try to learn something that we didn't know before. So I contend that trying to know something you didn't know before, making a discovery, right, banishing the darkness to a further corner, does actually indeed have emotional power. And using this description, I think it is pretty easy for me to show that both science and art are very, very similar, if not quite the same. And so, I'm a nerd, so I make flowcharts. If you want to do art, and in some cases, and in the same case you want to do science, right, you have to have some of the same components. So you have to have an artist. You have to have somebody who is actively engaged in their imaginative and creative process. You have to have somebody working on something. You have to have a subject. It doesn't have to be a real subject. It can be theoretical, or it can be an idea that you're trying to express in a new and different way. You have to have some kind of medium that you're using to express that idea, right? What tools are you using in order to get these ideas across? And the medium is part of the message. If you change the media, then you will change how the message impacts the audience, right? Artists have to have an audience. Somebody has to see their art or it doesn't exist, really. Scientists have to communicate their findings to others, right? It's part and parcel of what we do. You hear about all these conspiracies with scientists keeping information to themselves. Anybody that believes that has not met a scientist. You go to any meeting and we are the gabbiest bunch of folks you will ever meet. And we are talking about all the stuff we're doing before we have it published. I'm surprised that, people don't publish papers on other people's work, but we're all talking about it all the time. We want to share it with different people. But you have to think about, and I hit the wrong button there. You have to think about who your audience is, because you explain things in different ways depending on what audience you choose. I am not giving the same presentation today that I would give to my peers. I am giving a presentation for people who don't work with magnetohydrodynamics equations day in, day out. How many people do that? Just me. All right. All right. Well, the sun. This is my primary focus of study, is the sun. And everybody asks me, why do you study the sun? It's so boring. It's been around for forever. Well, that's not quite true, but it's been around for, as long as people have known to look up in the sky and see that big warm thing. And this is actually considered to be an exciting sun. Do you know why this sun is exciting? It's got little black spots, right? So the sun that people think of is just this bland yellow ball in the sky, and sometimes it gets little dots on it. How dull is that? Well, this is the sun we know, right? This is the sun and the wavelengths of light. And whenever I say wavelengths, I want you to think of colors, right? Wavelengths are how scientists measure colors. A wavelength of light is a very, very, very specific color of light that I can measure mathematically, right? So these are the wavelengths or colors of light that can actually pass through the Earth's atmosphere and can make it to the ground for us to see them. Therefore, our eyes have gotten to be very good at seeing these colors of light. But like so many things in life, if you take something that you see every day and take for granted and look at it in a slightly different light, all of a sudden the picture changes and you can appreciate it in ways that you've never appreciated it before. So all of these images were taken at the exact same time, right? This is the exact same sun. The only difference in these images is in what wavelength or color of light that we're looking at. So this is the visible light sun, right? And this shows an area of the sun that we call the photosphere. So it's like the surface of the sun. The sun's a big boiling sphere of plasma, not gas, but we can say gas, big cloud of gas. But here it's pretty solid. You go above it, though, right? So above this layer, and then you get to this layer, which we call the chromosphere. And we call that the beginning of the sun's atmosphere because it's much thinner than the photosphere below it. Now, visible light, we're talking about 6,000 degrees. We go up here, and now all of a sudden we're talking about 100,000 degrees, right? So getting warmer. Then we go a little bit further out, and now we get into the corona, right? And there's this thin region where it transitions from the chromosphere, this orange layer that I'm showing here, to the corona, and this is 1,000,000 degrees. And then this is the same corona in 2,000,000 degrees, and another image of the corona even hotter, all right? So these are images of the corona. This is actually an image of the magnetic field of the sun. So this isn't directly taken by light, but this is taken by some information we know about light. And those wavelengths of light can split when they're in very strong magnetic fields. So if we measure how much light splits, right, then we can measure what the strength is of the magnetic field of the sun. And you can see that the magnetic field is concentrated in these regions of black dots. And these regions also correspond to these bright regions in these images here, all right? So these images are taken in a very, very special wavelength of light, right? That wavelength of light we call the ultraviolet part of the spectrum. Extreme ultraviolet light. So what is extreme ultraviolet light? Well, everybody's familiar with ultraviolet light, right? It's the stuff that can give you a suntan or sunburn if you're not careful, right? And everybody's familiar with X-rays, right? That's what the dentist uses to look at your teeth, right? So when you go to the dentist, right, and they put you in the chair and they put all that stuff in your mouth to, reflect the images, what happens to the person that actually operates the machine? They leave the room. You bet they do, right? And they put you in this big lead thing, and then they run out of there, right? Well, that's because X-rays are so energetic that if you are exposed to them enough, your chances of cancer get higher and higher. To avoid ultraviolet light, because if you get sunburned too many times, your chances of getting melanoma, another form of cancer, also gets higher and higher. So this extreme ultraviolet light is in between the two. It's not quite as cancer-causing as X-rays, but it's more cancer-causing than UV light. So it's a very, very good thing that our atmosphere actually blocks out that light, right? Because if it didn't block out the light, we would be in a very, very bad situation. So in order to study the sun and these EUV wavelengths of light, we can't do it from the ground. We just can't. We have to put our telescopes on top of a spacecraft and send it above the Earth's atmosphere. Now, these telescopes that we're showing in this little animation here are called the Atmospheric Imaging Assembly, or AIA. They are a suite of 4 telescopes. They were actually built here in Cambridge by your wonderful Smithsonian Astrophysical Observatory, right? Some friends of mine worked on this project, and they were placed upon a satellite called the Solar Dynamics Observatory and launched into space. It was just actually had its anniversary launch last Thursday. It was its 6th anniversary of launch. So we've only been able to study this corona, this super hot atmosphere of the sun in extreme ultraviolet since the beginning of the space age, so about the 50s, right? So this is actually the least known part of the sun, except for the core and the interior, which you can't peer down into unless you know some special math. So that's why the sun is not boring, and it's definitely not boring to me. It is actually a living thing with moods and is dynamic and not just a yellow ball. Now, my subject is the sun, but but the way I view it isn't just with my eyes, it's in data, right? So I collect all of the data from these telescopes, all the information, and there's a reason for that. So this wavelength of light is actually ultraviolet. You can see a little bit of it from the ground. But the other ones I showed you, you cannot see these wavelengths of light with your naked eye, right? If you looked at the sun and were exposed to these wavelengths of light, you wouldn't see anything, right? Because light never came down to the Earth, and our eyes never adapted to see it. In fact, shortly after viewing that, you probably wouldn't see anything ever again, because again, super cancer, right? So we don't look at it, but what we do is we have those telescopes have special detectors, right, that look at very, very, very narrow wave bands, so just a very few wavelengths, very specific colors of light, right? And then they turn all that light that's coming in into a series of numbers, which then gets piped down and sent to us to study, right? It's a lot of the same technology that's in your camera phone, so nothing too sophisticated. But these images are huge. So the Atmospheric Imaging Assembly, AIA, is the first telescope to look at the sun with such great resolution to look at the entire sun 24/7, 365. Right? The size of these images are 4,000 pixels by 4,000 pixels. Right? So it's not 4,000, it's 4,096. So 4K by 4K. So what does that mean? Well, have you seen these fancy schmancy HD TVs? Right? You can't show one of these images on one of these TVs. In fact, you can't really show it on 6 of these TVs. You need more than 6. To get the full image, you need 9 HD TVs. You know, the even fancier 4K TVs that everybody's trying to make you buy, even though you just spent money on the HD TV, right? You can't even show these images 100% on 1 or 2 of those, because it's only 4K in one direction. It's not 4K in the other direction. So you need multiple monitors if you want to show these pixel for pixel, right? That's a lot of data, right? So the 4 telescopes end up taking 8 images of the sun, 8 different wavelengths, right? every 12 seconds. 4,096 by 4,096, 8 of those guys every 12 seconds, 24/7, 365. And that leads into some interesting issues. Like not knowing how to use your pointer correctly. All right, I'm not going to show many graphs, right? I promise you there's no math in this presentation. Well, not much math, but just a little math. You can do it. All right, but this is the only graph I'm going to show. And this is just a series of different missions, different solar observing missions. And here we've got the years, right, that the mission started. And here we've got the lifetime data volume in something called petabytes. So a petabyte is 1,000 terabytes. If you've got like a nice desktop, it's probably a 1 terabyte drive, maybe a 2 terabyte drive. If you got a nice laptop, it's probably 3/4 of a terabyte. So this would be like 1,000 laptops, right, worth of data, right, is 1. So that's 1,000 laptops. So that's the way you think about it. So here's where I started my career, working on an instrument called TRACE. And the data volume is not just shown by how high it is on this graph, but also too by the size of the dots. So I started here, and I worked on this guy a little bit, and worked on Hinode, and we went from here to here in a very short span of time, right? We're talking about multiple petabytes of data, right, in a short amount of time. The problems with receiving, encoding, transmitting that data are many. But the idea of actually analyzing that much data, for human beings to think about it, it is literally drinking from a fire hose. There is no way that we can get through that much data. In fact, when in the days of this mission, when I was a graduate student, right, the way that you picked out interesting things on the sun was you locked a graduate student in the basement to go through the day's files, and they would tag what was interesting. If you did that with this much data, right, it would take longer than the lifetime of a graduate student. Not the lifetime of their career as a graduate student, the lifetime of the graduate student to go through. So one of the projects I worked on early starting off in the CFA was actually trying to get computers to try to do a first swipe at this information, a first look, and say, hey, you might think this is interesting. And that work is actually ongoing, and I think that's actually the future of the field, or part of it. So I've told you how big it is in petabytes and stuff like that, but you don't really feel what petabytes are. So let's put in something that we know, right? So how big is this solar data in Blu-ray DVDs, right? So not the little DVDs, no, but this is like your 3D super Blu-rays, right? So a Blu-ray holds about 50 gigabytes of data, right? So if you do the translation, 1 day's worth of data is about 3 terabytes of data a day, right? 3 terabytes of data a day. That is 60 Blu-rays worth of data. That's a lot, but that's manageable. We can do something with that. We have a library. You know, we can store them there. All right, but that's 1 day. 1 year is 21,000, almost 22,000 Blu-rays. Now we're starting to get into where maybe you might have trouble imagining what that looks like. So I decided to change units, and I changed it into minute bowls units. So if you were to stack up DVDs, no case, just one on top of the other, and just stack them up, they would be slightly taller than the tallest NBA basketball player to ever play, Manute Bowles. Okay, well that's starting to get a lot. That's a year. We have 1 Manute Bowles worth of data. The mission so far has been going for 6 years. Like I said, it just had its anniversary. So how much data is that? Well, I went back and I had to get a new unit of measurement. If you look at how many stories it is of data, right, the number of DVDs, just stacked, no case, one on top of the other, is just over 3 stories. So you could actually have a stack of Blu-ray discs that's taller than the building you just entered today. Now, the mission's ongoing. The sun has got a cycle of 11 years, right? And we've been observing it for 6. We would really like to observe the sun over the entire 11-year activity cycle. So what happens when we go to 12 years? Well, we double the amount of data, and it is just shy of the whole thing. So, a lot of data. I think this kind of visualizes some of the problems that we have to go through. Think about if you had to watch every single movie, extras and all, commentaries and all, for 263,000 movies. That is the data that we are hoping to have. That is what we have to go through to parse and to understand. And one of my main jobs is to try to translate the numbers in that much data in a way people can understand, like using graphics and pictures of minute bowls. All right, so I'm the artist, the scientist. I've talked about what my subject is, and now I'm going to talk about some of the different tools that I use in order to interpret that subject. Like I said, we can't see extreme ultraviolet light. So what we have to do is we have to add color to these images. And we use these colors to try to understand what that data is trying to tell us. Now, this is an image of the visible light sun. And we're going to go from an image of the visible light sun, and watch the spots. We go to that. So we go to about a 2 million degree sun. And you see where there was once sunspots. Now there are all these loop structures, right? We call those active regions. Now we're looking at multiple temperatures at once, multiple colors at once. And all of these different colors actually interact with each other. And then we overlap the magnetic fields on top of those images. So by using colors, we can learn how one part affects another part, right? Sunspots, active regions, multiple wavelengths. Each wavelength actually represents a temperature that we're looking at, a temperature of the gas that we're studying. So multiple wavelengths, multiple temperatures, and now we add how the magnetic field is put into them. So instead of just looking at the bare numbers, we as humans actually colorize the images and look at them and color code them. And that's because humans are primarily visual creatures. We've been designed to process visual information very effectively. But the question I always get is, oh, well, you added color, so those are false color. You faked the data. You put false color on. It's like, no, not really. All of the numbers, all of the colors, everything I've shown you here, even though we made choices about which colors to use, right, it still represents the data below it. And the example I really like to use is a paint by numbers set. All right? So this is a paint by numbers kitty. And if you're not familiar with paint by numbers sets, what you have is a series of numbers in different regions, and then you have a legend. And in that legend, right, it tells you which color to put with which number to form a picture. Now I'm going to do something very dangerous. I'm going to get out. We'll see how this goes. So here's a picture of Kitty. All right. Now, I'm not going to change anything about Kitty, but I'm just going to play around with the colors a little bit. So without changing any of the information, without changing any of the underlying numbers, right, by making some choices about the color, I can choose how I represent those numbers. And I can use that to enhance some features or de-enhance others, depending on what I want to find. But the underlying numbers stay exactly the same. And that's one of the take-home messages that I want you to get. Yes, we are using the data. Yes, we are manipulating it. We're adding colors. We're looking at it in different ways. But the numbers underlying all of those choices, the subject matter, is the same. But we as scientists are making choices in how we represent that data in order to make new conclusions. Again, we're making choices of how to represent a subject using a specific media. Again, I think the connections to art are clear. Now, so we can choose some colors and stuff because we're visual, but we can choose a lot of other techniques. And, you know, we're nerds, astrophysicists. We love our math, right? And so we have learned a bunch of really, really funky math that we can do on images for image processing. This is an image of the sun that a colleague of mine was looking at. And they saw all these strange ripples that they didn't understand in the outer atmosphere of the sun. Again, this is the corona. This wavelength of light that we're looking at corresponds to about 1 million degrees. Everybody asks me, what unit of measure are you using? I say, it's 1 million degrees. It's hot. It really doesn't matter. But these are Kelvin. These are Kelvin. And you could see all the structure and rippling, but we couldn't see it that clearly. And that's because as you get further and further away from the sun, things get fainter and fainter because they're less dense. So what we did is we applied some math and we made a special kind of filter just so that we could study these regions. So these images of the sun are actually of the exact same time, the exact same data. We are just choosing how we represent that data. And these are actually synced in time, so you can see how these look the same and different, right? And remember, we wanted to focus and see all this stuff here, and you can see that we've enhanced everything that's going on there. So now we get a clearer picture of these ripples and waves that we did not understand, and we're still actually studying. This is a filter you can make. Remember I said there would be a little math? All right, here it comes. I'm going to tell you how this filter works. This is called a radial filter, all right? And what we do is this part of the sun here, you see there's a little black line? This part of the sun we haven't treated at all. So this should look just like here, all right? But what we did is as we went away from what we call the limb of the sun, right, the edge, as we went away, what we did is we drew a series of circles around the sun. And what we did is along every circle around the sun, we measured how much light was hitting the detector all around that circle. Right? And then we found where that number was the biggest, the maximum, and we divided every number around that circle by the biggest value. It's a process called normalization, right? And it's where you make everything on a scale from 0 to 1, right? Because 1's going to be your biggest number, because you took the biggest thing, you divided everything by that thing. When you divide it by itself, it's 1. Since it's the biggest thing, you're never going to have anything bigger than 1. And we did that for a series of circles extending out so that things weren't scaled to the absolute brightest thing. They were scaled to the brightest thing at that altitude. And we were able to really enhance features that you wouldn't have seen just looking at the data just in a standard way. We have not faked the data. We have not moved. The numbers are the same. We have just chosen to represent it in a different way, and now we can notice things that we didn't notice before. Again, it is the process of using creativity. The hardest math in here is division, right? You can do division. But that's the hardest math. But it was the creative application of that math to a problem that allowed us to have these images. All right. So I've talked a little bit about the media. And the media that I typically deal with are color scales and then data analysis, what math we apply to it. Now I need a canvas. I need a way to actually get that out of the computer hard drive and express it to people. Right? And the way that I've done this is in a very visual way by showing images and movies of the sun. Now I do this because one, they're just powerful images. They're beautiful images. I'll show you, I'll have some beautiful shots for you later that you can just gawk at. I do every time. But here's an image of the sun, and actually representing it in a visual way is very powerful for most, but not all people. Now, why did I do this? Well, as Christine said, my research and what I did my graduate research on was actually simulations of stuff in the sun. And here is a picture of one of my simulations. This is a blast wave from something called a supernova, right? So it's the sun that's dying, explodes, and the blast wave is actually shocking through a bunch of little cloudlets. Calculations like this one take a lot of computing power, and you really have to do them on supercomputers. But supercomputer time is valuable, so I needed to run a couple of test cases to see if my code was working before I put it on supercomputers. But I didn't have the money to build a very expensive computer that would need to do that. It would have taken many tens of thousands of dollars to do that, and then supercomputers really millions of dollars. So I figured out another way to make those same calculations using tools that were already made. Not many people realize this, but the gaming industry has now surpassed Hollywood in total revenue. It is a multi-billion dollar industry, and they are putting billions of dollars into research for these things called graphics cards. Now, if you're not familiar with graphics cards, they're a computer inside your computer, and they change a bunch of math into images in near real time. Well, 10 years ago, I figured out, hey, graphics cards, I can buy a really powerful one that does as many calculations as a small mini supercomputer for $300 instead of $30,000, $50,000 if I just know how to use the power of that card in order to make those calculations. And so I did. And I learned how to use graphics cards in order to do scientific calculations. Now again, I wasn't the first to do this, but it was new at the time. But there's a company called NVIDIA that really pioneered the field, and now they actually make video cards that do nothing but compute. And you can now get a many teraflop computer, which that's big. Just think big. And you can get that for cards that cost on the order of $3,000, whereas if you were to build that system using traditional technology, it would cost you many tens of thousands of dollars to do. So I took tools made by the video game industry in order to do my calculations, but they're still video cards, so I got to be good at knowing how video cards work and how to manipulate them. We had these large images, and so I used my knowledge of video cards to build a video wall in our Science Operations Center. Now, somebody tried to do this before. It turns out that it's more complicated than you think. A colleague of mine came up to me not too long ago and said, so basically you've turned your career from doing advanced mathematical modeling to putting videos on TV screens. Brilliant. The problem is technically actually more challenging because when you have multiple screens, you have to think about a lot of things. You have to think about how they sync up. You don't want one movie going faster than another to start a few seconds before. All the colors have to be balanced in the same way. There's a lot of different details that you have to go over. So it's not just putting video on TV, but it's actually close. But these images are so startling, right? So here is a video wall. These are all HD TV screens, and you can see we've got 9 of them, and we can just barely start fitting the AI data on these screens. So the colleagues that also made fun of me like having their photos taken by my video wall. This is a photo of a good colleague of mine, Justin Casper. Justin, if you're watching, hello. He is the PI of an instrument that's going to be on Solar Probe Plus. It's an exciting mission. Solar Probe Plus will actually dive into that atmosphere of the sun I was talking about, the corona. It will get closer than any object human-made has ever gotten. It will have temperature differentials of many hundreds of thousands of degrees within millimeters. So it is in an extreme environment. And his data produced plots that look like this. Boop, boop. Notice he's not standing next to a picture of a plot, right? That his data look. He's standing next to my video wall, so, a little bit. So, this is the way our science display looks pretty much every day if you go down. We've got one large image of the sun looking at 1,000,000 degrees in the corona, 100,000 degrees, 1.2 million degrees and hotter. And we have this up because we control other satellites from our operations center. And those satellites are more like microscopes. This is the only mission right now that looks at the sun this much detail and looks at the whole sun, right? And we get these images 24/7, 365. Other instruments can look at little regions of the sun at a time, and you have to plan them at least a day in advance, sometimes several days in advance. So we use these images to determine where we're going to point our instruments the next day or the next week. And we use it to actually zoom in and find interesting features. Now, anybody watch NCIS? Nobody's going to admit to it? Good. All right. So data visualization scientists hate shows like NCIS, right? Because they'll take like a picture from an ATM, and they'll look around the corner from that picture, and then they'll see a license plate, and there'll be like this picture with like 6 pixels, and then they zoom and enhance, and then all of a sudden they can read the license plate. Yeah, that's bogus, all right? You can't do that, right? But these images are actually so good that we can actually zoom and enhance. We can look at the entire structure of the sun, and then we can see these smaller scale features of the sun, and these small features actually affect the larger sun as a whole, right? If you were to look at these images on your laptop screen, right, you could either fit the whole sun in your screen, but you'd have to shrink it down so much that you'd lose that fine detail so that you could see all these little things going on. But if you were on your laptop screen and you zoomed in so that you could see these small features in detail, you would lose how it affects the sun as a whole. So creating these video walls was actually a scientific tool. It's a tool in order to help our planners plan, but to investigate solar phenomena in a way that this instrument, like no other, allows us to. Well, I say that, and here's one of the phenomena that we studied in this way. So this is famously called the coronal rain movie. So what you're seeing is the after effects of a solar flare. Solar flares are large explosions on the sun, releases many hundred thousands of years worth of entire world energy uses. Instead of 100,000 years, it releases as much energy as the entire world would use in 100,000 years in about 5-7 minutes. More energy than all the thermonuclear weapons ever built by humankind. Times a factor of about 300,000 to 1 million, depending on the size of the flare. Small ones aren't quite that big. But these are really powerful images. So we're looking at different colors, different wavelengths, and we're seeing different things. The images go from hottest, not quite so hot, cooler, and then coldest. And what you'll see is the flare actually will brighten up, and then all this material gets launched into space, and then as it starts to cool, it'll start to flow down, and you'll see it forming these beautiful, beautiful arcade of loops. So this movie is just pretty enough that I have to show it a couple of times. So here's the flare going off, right? So boom, that's all the energy going off, everything's getting thrown up. As we're watching this beautiful movie, I want to point out, you see that little blue dot? That's the Earth for size scale. So you could fit about 4 or 5 Earths underneath that arcade of loops. All right? That's what I get to do every day. I am a lucky, lucky man. All right? But having these data visualization tools allows us to study these in new ways. However, I kind of knew what I was doing, and I knew how beautiful these images were, and I knew how much of an impact, well, I thought they'd have an impact on lots of people. And this is another exercise in scale. There's the Earth to scale with the sun. This is, again, the video wall that I built for our operations center. And to scale the video wall, this is my supervisor, Ed DeLuca, who's about 6 foot and change tall. So it's this beautiful, large format thing that you can go up to, you can get close to, and see all these features. And that is just amazingly powerful, especially when you realize the size of everything you know compared to your subject, right? It gives you a new outlook on your place in the universe, the size and scale of the universe. And for me, that's emotionally powerful. So using that video wall, I was able to talk some museum people into coming and visiting us at the CFA, and they fell in love with the imagery. And this is the first project that I worked on. Our science education department did most of the work on it, so I don't want to take any credit away from them. They did the heavy lifting on this. But we provided a series of solar images for this exhibit. It's called The Night Sky. It was at the Boston Children's Museum. Here is, again, the Earth to scale. This is Venus actually transiting across the sun. And I absolutely love this exhibit, right? So this is a kid interacting with it. And I love this exhibit because you can interact with the data. You can actually get a feel for how the data is. There are all these buttons here, and they're rigidized. They're very hard, they're very sturdy buttons. And each one's got a picture of the movie that you're going to see along with text. So kids of all ages can look at these different buttons and whack it as hard as they want to. You're not going to break it, and watch different movies. And this kid is actually playing with this center wheel, and by manipulating the wheel, you can make the movie go faster and faster and faster, or you can stop it and have it play at normal speed, or you can spin it around the other direction. You can make the movie go backwards. That is fantastic. The kids loved it. I think you can see how much this kid's into it. What you can't see is the line of adults behind this kid, right? Elbowing each other, but fortunately not elbowing the children out of the way at the Children's Museum. So I think I've proven the point that these are actually things that can impact people, not just from a scientific way, not just from an educational, lofty way, but really on an emotional level. It's fun to do these things. It's fun to play with them. The second exhibit that I did, and this was primarily my work, a colleague Mark Weber helped me with it a lot too, was an installation at the Cooper Hewitt National Design Museum. Now, this is a museum that is based on design, right? So it's this intersection of art and form and function. And it's in the Carnegie Mansion in Manhattan, right next to Central Park. And they had been closed down for 5 years for renovation. They wanted to have an exhibit based on tools, extending our reach. What tools we use to extend what we can do as humans to do more than we could without tools. And my tool was not only the solar wall, which I used to present this data, but also to the instrument. But it wasn't just about trying to get knowledge across, it was actually about art and form. So this is an installation, this picture's kind of ruined by some weird guy standing there in the center, but this is an installation by a very famous artist called Damien Ortega. Now Damien is well known for doing exploded views of objects so that you can see them in a way that you're not used to seeing them. His most famous work, which was actually showing at the ICA for a while, it's an exploded view of a Volkswagen Beetle, one of the old ones, and everything hangs by these very, very thin, clear wires. So you can't really see the wires. Everything looks like they're suspended in space. This one's called Controller of the Universe, and the idea is that you walk through this piece, and along every eye line, you see there's a different tool that you look like you could reach out and grab and use it to help master the universe you live in. Now, security doesn't actually let you do that. I know, I tried a couple of times. They're just, he got these at garage sales, right? He is an artist, he made this, it is art. But I actually love this piece a lot, and it looked really good with the video wall behind it. So this wasn't for scientific purposes, this was just purely 100% to enjoy, for people to have a different experience with. Now, this is the exhibit that I did last year, and this is definitely the most seen exhibit I've done. This was at the National Air and Space Museum on the National Mall. I built a video wall there that actually shows real-time data, near real-time data coming from the satellite, and is being projected on that video wall. We also have a few best of movies. I'm still working with their education department. They were so excited about it that now we're doing new programs, trying to make new content by it. And this is part of an exhibit, and this isn't just about design. This is about how knowledge starts at one place and it builds upon itself and builds and builds and builds. One of the first telescopes to image the sun and these extreme ultraviolet wavelengths was on an old space station called Skylab, right? And this is an engineering mock-up of Skylab. And the telescopes were mounted at the top. And then there's a little piece here that shows how, all these different instruments and how we've observed the sun from Skylab, until present day with this mission. Now, I'll let you know a secret. As a kid, I got to go to the National Air and Space Museum, and they had to drag me out of the Skylab because I wanted to be an astronaut. You can go in there and you can see these little claw marks from where I tried to hang on. I didn't get to stay there. I didn't get to live there. But I did make an exhibit that is right next to one of my favorite places on Earth. That is not my favorite moment about this exhibit. It's close, but it's not my favorite moment. This is my favorite moment. We had a lot of technical issues with the wall. It's not just as easy as putting video on TV. Lots of things went wrong, lots of things to do with the feed. And we finally got working the day of the grand opening. And there are these barriers in front of it, but we finally get it working. I've been up all night, and I wonder why I do these stupid things. It's not like they pay me extra to do it. And we pull away the barriers so that they could take some press photos. And the very first thing that happens, the very first thing that happens, this young woman comes up. I'm not good at estimating ages, but maybe 13, 14. She goes up, and she says, "Wow, that is so cool," and pulls out her cell phone and starts Instagramming it, Snapchatting it to everybody she knows. Tell me I'm not winning life at that point. Right? Aren't they supposed to be jaded at that age? I mean, you're not, but aren't the rest of them? Right? If you know anything about science education, right, the aptitude to do science, it's equal, male and female, right? There's no difference here. But the interest in science is the exact same until about 7th or 8th grade. And then you see the divide. You see this terrible drop-off where societal pressures, for some reason or another, say, well, science is for boys, not for girls. I hate that. I'm trying to change that. I hope in some small way this changes it, and that she will remember that time. I have no way to prove it, but it's a hope. The other thing I like is that people send me pictures from the Air and Space Museum all of the time. So this is a picture that a friend of mine sent. This is actually his grandson. He took his grandson to go see it, and I think there are claw marks away from the exhibit again. And again, I think that these images are just powerful. So this isn't really a high-resolution shot of the sun. This is just taken with a cell phone. I do want to point out, so I always put the Earth to scale. So again, this is a choice I've made, because I don't want to clutter up these museum exhibits with text. But I would like for somebody to learn something from seeing it, not just enjoy something pretty, but to learn something. And I think you can learn something about size scale, right, without any text, without any word. You see the sun, Earth, sun to scale, and then you see the sun. And all of a sudden, you just know something. Without reading, you deep down know something you didn't before. Now, notice that the other images I showed you didn't have a box around the sun. That's because they came before a focus group I did. And I don't know everything. I try to convince people that I do, but I don't. And so I ask questions all the time. That's what I'm supposed to do as a scientist. And so when we started doing the video wall displays for this and started designing the content, started making the choices about the medium and how we were going to represent the subject of the data coming from the sun, I showed a movie much like this one with an Earth without a box in it. And then I took some questions before and after of just general people, just people off the street, and asked them what they'd learned. And one of the things that they said that they learned is that they didn't realize that the sun wasn't just a yellow ball, that there was more to it than that. Yes. They didn't realize that the sun was dynamic. It had all these things launching off and erupting and these arcades raining things down. Yes. They didn't realize how large the sun was, right? And seeing the Earth compared to the sun, right, it made them realize how large the Earth was. Yes. The other thing that they said that they learned is that they didn't realize that the Earth was so close to the sun. All right. The one thing I don't want to do is I want to increase knowledge. I don't want to increase misunderstandings. And when you put something up there and you superimpose something for size scale, people just looking at it, not thinking maybe too much, because this is not something you're supposed to think about deeply. This is something you're supposed to view and appreciate. But you get size scale and distance scale confused. It turns out something as simple as just putting a white little box around it, since boxes don't occur in nature, since you don't have right angles in nature, they see that little box and they go, oh, that's artificial, that's superimposed. I don't have to tell them that. They just pick up that visual cue and they know. And so just putting on that box actually got rid of that last wrong answer, right? And so that made me very happy. This is the most recent picture. I actually just got this last week. It's kind of blurry because it's from a cell phone, but I'll just tell you why I love it. They're just all these kids sitting around and just watching the video wall. And evidently, this happens all the time. And if you know anything about, I didn't know anything about museums. All right? I didn't know anything about museum exhibits. I've been learning on the fly, right? I'm a scientist. That's what I love to do. I love to learn things I didn't know before. So here's something about museums I didn't know before. The average dwell time in an exhibit, the average time that a person goes to an exhibit, stands and looks at it, is about 30 seconds. All right? So not very long. And this is, again, why we try to design what information we put on the exhibit, right, so that you could kind of process it quickly. So 30 seconds. Some of my colleagues at the Air and Space Museum have been sitting around with stopwatches, and from their anecdotal, not really scientific, but from what they've measured, the dwell time on this is about 1:30, right? So about 3 times the average. Still not a long time, but much larger than the average. And if you're sitting down, you're there for the whole show. That makes me very happy. All right. So I am not the first person to do this. I don't want people to think that, oh, Trey put colors on data and how smart he is. I'm not. Lots of people are doing this. And one of my colleagues that I heard a talk from, and I was just completely impressed by her and constantly am. Her name's Michelle Borkin. She did a TED Talk. Astronomers help doctors. If you just Google that, you'll find the TED Talk. Don't bother writing this. But she was working with a series of doctors in order to help them diagnose heart disease, right? So cardiac surgeons, by using these 3D images. And it turns out that the doctors weren't doing a very good job by looking at these 3D scans in order to interpret what was going on. By doing something as simple as changing the color table, changing the colors, right? Using the same paint by numbers, but changing the legend about where each color went in the box, she was able to drastically improve their ability to diagnose a problem in the heart without having to cut somebody open. That is the power of data visualization. That is the power of thinking about not only presenting the data, but thinking about how your audience perceives that data. Yes, it's art, but also, too, it serves a purpose. And in this case, that purpose is saving lives. Oh, one of my slides got out of sequence there. This is the latest exhibit I've done, and I just did this last week. So this is at the NCSU Hunt Library. They have a series of video walls at the library, and they call them the beasts because you have to constantly feed the beast. You have to constantly find content. And for video walls of this scale, it's hard to find content that actually looks good at that scale. Now, I opened this last Thursday. As Christine told you, there may have been another news event that happened last Thursday. I'm actually good friends with several of the LIGO people, and I talked with one of them the next day. And I said, you guys have been waiting for 25 years. You couldn't have put it off one more day so I could have blown up Twitter. And they said they basically planned it around my schedule. So, this is the director of heliophysics at NASA giving a talk about heliophysics at NASA. And in this space, in the museum, so this is the Commons area, and you can see that there are galleries here and here. We had about 200 people show up, right, on a Thursday night, beautiful weather, sort of, to just show up and hear us talk about the sun and look at these images of the sun. Again, I think these are amazingly powerful, but this is why I do it. I really love talking to people about what I do. I really love communicating my love and passion for what I do. And I like this picture a lot because it shows how much fun I have doing it. It also shows that I'm not the only one laughing at my jokes, that sometimes other people enjoy what I have to say too. But I got to meet a lot of great students that aren't just doing science, but I got to meet with a bunch of design students, a bunch of 3D artists. And I've been getting email from dozens of students, not in science, but in design and artistry, to talk about how we might work together on different projects. And that just makes me incredibly happy. I did want to give a shout out to one of my colleagues, Kim Arkan. She does a lot of work with the Chandra mission. She's got a new book out, and it's all about investigating light. So all the things I've been talking to you about is like how I'm representing the light we get from the sun in new ways. And that's what astronomers excel at, because that's usually all we get from stars, is the light. And Kim, along with some colleagues, has done a lot of work on studying how to make those representations something that people will understand and that can catch the imagination of the general audience. So again, I'm not the only one doing this. Lots of people are doing this. There's lots of different examples. And of the people doing this, you can do it too. So NASA's got what we call an open data policy. That means you've already paid for the data, so it's all open to you. Thank you for your tax dollars. I appreciate it. It helps me pay my rent. But lots of images are now online and that you can get them. So you don't have to memorize the entire URL. Just Google SDO gallery, right? That's the name of the satellite. SDO, sun, stuff like that, you'll find it. And you can download hundreds and hundreds of curated images and movies like the ones I've shown and like the ones I'm about to show. And you can watch them to your heart's content. But these are curated. These are the ones that they thought are interesting. What if you don't think they're interesting and you want to play with the data yourself? Well, we've made that possible for you too. This is a project from a friend of mine named Jack Ireland. Jack spent a bunch of time taking all the complicated math that we have to do to turn all that information into images and made it available to you. All right, now I'm going to do something dangerous. So I'm going to pop out of the presentation again. This is fraught with danger. All right, we seem to have success. So This is a HelioViewer. This is the tool that allows you to access data. And I am accessing this real time from a web page. So I can make the sun bigger. I can make the sun larger. Here's my favorite thing, the Earth to scale. Box. Notice box. And I can not only just, so this is that chromosphere I was talking about, 100,000 degrees. I like stuff a little hotter. So what I can do is I can add another instrument, another wavelength of light to this. And I'm doing this all real time, so this is just all point and click. So SOHO, AIA, and I think the 193 is going to look good. So this is all real time. So now I've just overlapped two of those colors, right? So I can see how they interact. And I can play around with the opacity, so I can make one stronger or dimmer. You see that? Oh, and wait. There's something cool. This is what NCIS can't really do. Zoom and enhance. Look at that thing. I can zoom in more. But I need to. So I can really bring out that feature up there. I did this all real time. And then there's another button here that you can press, and you can make a movie of it. You can go forwards and backwards in time. I'm not showing them here, but there are buttons for when you make a movie. You can put it up to YouTube. You can put a link on your Twitter, or you can download it to your laptop. You can share them on Facebook. All of this is available to you for the low, low price of you've already paid for it. Thank you very much. I love this tool. It's HelioViewer. You can find it by just doing a simple Google search, or you can ask me about it later. So all of this data is yours to play with. It's not my data, it's our data. And I've chosen some ways to view it and work with it, but you can actually be the artist in this game. You can actually have access to all of this beautiful imagery and do what you want to with it. Scientific analysis, art project, something pretty to put up on your wall. And I hope I've shown you part of my passion for what I do. It's not just the math. I'm really good at math, but it's not just that. There's also a beauty to this that I just really can't explain in words. So I'm going to let movies and images explain it for me. Thank you so much for letting me ramble to you for a while. My name's Trey.
We're going to take 5 minutes for questions and answers, and then send the people here in the room up to the roof. And the lady up front had her hand up first.
Okay, what's the best wavelength to see data for solar observations, otherwise invisible?
Okay. So the question is, what is the best wavelength to look at in solar observations other than the visible light? And the answer to that, was, as is true with so many answers in life, it depends. What do you want to look at? Where are you interested in knowing? Some features look one way in one wavelength of light and look different in another one. Some features you can't see in some wavelengths. You can only see them in a very few. Do you want to see cold things? Do you want to see hot things? Right? A lot of what I do is I see how the hot interacts with the cold. So I don't use just one color. I have to use multiple. So again, going back to one of my main topics of this, it's a choice that you have to make. There are, with AIA, there are several choices. We take 8 images every 12 seconds, right? So you've got 8 wavelengths you can always play with, plus a few more. There are satellites looking at the sun in X-rays. There are ground-based telescopes looking at the sun in visible, and all these different wavelengths. You have almost the entire electromagnetic spectrum, from radio waves to X-rays, to play with. The question is now which is the best, but what you want to do.
Yes, sir.
How old is the sun and how old will it live?
How old? Okay, so the sun's a middle-aged star, right? We're creeping up upon the 5 billion mark. We've got about another 5 billion to go. So the sun is a middle-aged star. It's about an average star. We got about another 5 billion or so in life. Don't quote me on that. It's about that number. It might be a day or two off. Everybody asks me, oh, do we have to worry about the sun going out? And a lot of things that happen on the sun actually do affect us on Earth, right? But the sun going out is not going to happen for many, many billions of years. There are storms on the Earth that can cause, storms on the sun, I should say, that affect us here on Earth. In fact, there's that period of time I was telling you about, the 80s, right? We had this president called Reagan, and it was the time of the Cold War. Russia wasn't Russia, it was the USSR at that point, and we weren't really friendly with them. And they were undergoing major changes, and the President of the United States was on Air Force One over the Pacific, and all of a sudden went out of contact with the Pentagon, right? The Pentagon doesn't like it when they lose their president. And they lost the president for hours, right? They didn't know if it was a missile attack, they didn't know if the plane went down. What could it be? Turned out it was a storm on the sun, right, that propagated through space, impacted the Earth in such a way that caused problems with radio communications in a way that Air Force One had lost signals. This is one of the major reasons why the Air Force now gives me some money to study the sun. And the Air Force money I take is all for open science. It's like nothing secret or anything like that. It's all just to understand the sun better and to be able to predict these things better. So there are things on the sun that can affect us here on Earth. Don't really need to worry about it going out. We got billions of years. You can plan your travel accordingly.
The young fellow up in the balcony there.
Young fellow in the balcony. Yes.
Does the sun have volcanoes?
Does the sun have volcanoes? No. The sun does not have volcanoes. Volcanoes,
Gas volcanoes.
well, so the sun does have places that erupt, right? And some of the physics is the same, some of the science is the same, and some is different. When we talk about volcanoes, we're talking about super, super hot rocks, right? So rocks that are so hot that they've become this liquid thing that goes boom and like goes up in the air and flows, and then when it gets cool, it becomes like metal and rock again, right? Well, on the sun, oh, how serendipitous. So this image of the sun here, right? It doesn't have volcanoes, but it has these things exploding on it all the time, right? And in the same way that a volcano takes rock and makes it super hot to make it a liquid, the sun, especially in this outer atmosphere of the sun called the corona, it takes things and makes it so hot, right, that becomes this thing called a plasma. Now, what you're looking at right now is super, super hot iron, right? Now, usually I make somebody look foolish and ask them what gas they're looking at, but in this case, I'll give you guys a break. But you're looking at iron that's gotten to be so hot that it's melted and become a liquid. But it's gotten hotter than that, it's become a gas. And then it's got hotter than that, right? It's not just a gas, it's a gas that has like protons and little electrons zooming around the room. It's gotten so hot that those electrons have like flung off and they're not coming back to the atom anymore, right? So it doesn't have volcanoes in the traditional sense, but it does have explosions. It does have super hot regions where it turned something that we think of as a metal, not into a liquid, but a gas, and a very special gas with very special properties called a plasma.
All right, and with that, we're going to wrap up the webcast Q&A at least. Thank you all for joining us, and we hope that you will come back for our next observatory night next month.